In classical probability, we have already seen that there are many kinds of events with which we are interested, as for example union of events and intersection of events and their corresponding probabilities. Now when we talk about the probability of intersection of events, then naturally the concept of conditional probability comes into the picture. Now we have already we have some idea about the conditional probability and some of its properties. Now one very related concept with that is the concept of independence. That means when the two events are called independent events, that means what would be the conditional probability in that case? That means when the conditional probability is exactly same as the simple occurrence of that event, we usually say that this event is independent. But in the context of measure theoretic probability, we have to define this concept of independence in a very rigorous way, because later on we will see that this concept of independence has an extremely major role in the entire theory of probability, especially related to the events of convergence in terms of some events and convergence of a sequence of random variables. Now this again will lead the path of many important theorems and properties with respect to several areas in probability theory. So today we are going to discuss this concept of independence. We are trying to formalize the definition in a very rigorous way and in a very general way, not only in terms of a particular event, not only in terms of a sequence of random variables, but also the question is, can we define independence in terms of some bigger class of events, as for example sigma field, or rather Borel sigma field generated by a sequence of random variables. So today we are going to discuss mainly the concept of independence in a very rigorous and a very general way. So our main focus of discussion is independence or independence of events in the context of probability theory. Let us start with a few definitions. Suppose omega, script f and p, this is a probability space. That means omega is the whole sample space. Script f is the sigma field generated by the class of subsets of omega, and p is the probability function defined on this omega and script f. Now consider a few classes of events, that is gt, let's denote this by g suffix t, which is a subset of this sigma field script f for every small t belongs to capital T, where we consider capital T as any index set provided T should be non-empty. That means T not equals to phi. So for any such index set we can find a small t for which we can define gt, where gt is a subset of script f. Then now we define independence in terms of this gt. So we say that g suffix t, where small t belongs to capital T, are said to be independent if for each m, now m can take 1, 2, 3 all these integer values, and each choice of t1, t2, tm all belonging to capital T. Now note that here we consider this t1, t2 and tm, they are all distinct. So for such choices of t1, t2, tm belonging to capital T, and we define aj, and for a set or for an event aj that belongs to capital G suffix t, for j equals to 1 to m, we have probability a1, a2, am, that means probability a1 intersection a2 intersection and so on intersection am equals to product of the probability of individual events. That means probability of a1 into probability of a2 and so on into probability of am. So this is the definition of independence at this moment. That means we are considering the independence of m events, where m is in this case for the moment finite, and each aj belongs to this gt. Now note that gt must be a subset of script f. Another important point to note in this case, if gt, t belongs to capital T, are independence as per the previous definition, then gt star where T belongs to capital T star are independent for T star when T star is a subset of T and GT star is a subset of GT for each small t belongs to capital T star. That means here defining independence in terms of a class of events G, capital G of T. Now we are saying that we can extend this concept of independence to a class of sets denoted by GT star, where GT star is nothing but a subset of GT. So this is a very general definition of independence. Next, when we decide on this independence of events, and we see that all these events are belonging to a probability space, or they belong to the sigma field, then naturally one question comes that can we define independence in terms of random variables? And naturally the answer is yes. So we define random variables x1, x2, xn are independent if the joint distribution function of these variables, that is joint distribution function of x1, x2, xn, that is capital F of x1, x2, xn, is nothing but the product of individual distribution functions. That means capital F of x1, x2, xn equals to capital F of x1 into capital F of x2 into capital F of xn. Well, obviously capital F of x1, x2, xn is a joint distribution function, and for j equals to 1 to n, capital F xj is a marginal distribution function of xj. So this way we can define the distribution function in terms of we can define independence in terms of distribution functions. Now note one important thing from our previous discussion, or rather previous lectures, that for any random variable distribution function always exists. So this is a very general definition of independence of random variables, because we have defined it in terms of distribution function or the joint distribution functions. Next, consider another definition which will be required subsequently, that is smallest sigma field or the Borel sigma field. So for a random variable x, we define the smallest sigma field containing all the sets of the form capital X less than lambda, that means as in minus infinity to lambda, where mod lambda less than infinity is called a Borel sigma field generated by x. That means for a random variable x, we can always define a Borel sigma field generated by x in the form of collection of all sets of the form x less than lambda, where obviously mod lambda less than infinity. And we denote this sigma field by script b of x. So whenever we write script b of x, this will always denote the Borel sigma field generated by the random variable x. And this will again play a very important role in clarifying the concept of independence. So now once we define this Borel sigma field generated by a random variable, we can think of another class, like for a family of random variables xt, where t belongs to any script, any capital T is any index set, then the smallest sigma field containing all sets of the form capital Xt less than lambda t, where t belongs to capital T, mod of lambda t less than infinity. This collection or the sigma field, the smallest sigma field generated by all sets of this kind of this form is called the sigma field generated by xt. T belongs to capital T, and this is also denoted by script b. So I denote script b of x small t belongs to capital T as script b of capital X suffix capital T. So this is just for the sake of simplicity in writing. So basically the idea comes from the previous definition. The only thing is that here we are defining this smallest sigma field by the class of, or by a family of random variables, which is denoted by xt. Now once we have defined this Borel sigma field generated by random variable, the question is, can we define independence in terms of these sigma fields? And here is one definition in this direction, that is script b of x1, that is Borel sigma field generated by x1 and the Borel sigma field generated by x2, these two are said to be independent if for every a1 belonging to script b of x1 and a2 belonging to script b of x2, a1 and a2 are independent. That means probability of a1 intersection a2 equals to probability of a1 into probability of a2. Now note one important thing, that this is true for every a1 belongs to script b of x1 and for every a2 belonging to script b of x2. So there is no particular choice for which this should hold for any a1 belonging to script b of x1 and any a2 belonging to the Borel sigma field generated by x2. And in that case we say if for any such events a1 and a2, or this probability of a1 intersection a2 equals to probability of a1 into probability of a2 holds, then we say that script b of x1 and script b of x2, they are independent. So we are actually trying to generalize this concept of independence. We started with the independence of two events, or rather m events, m is finite, and from there we defined the independence of random variables, and from there we define independence in terms of the Borel sigma field. So now another definition in the same line, there is a family xt, t belongs to capital T of random variables. So consider a family of random variables denoted by xt. This is said to be independent if x1, xt1, xt2, xtn are independent for every finite collection t1, t2, tn, which is a subset of script t. That means take any finite collection of numbers or suffixes from capital T, and if for such suffixes all the random variables are independent, and this is true for every such finite set, then we call that this family is a family of random variables is independent. Now this actually leads to one natural question, that although we have defined independence in terms of random variables as well as in terms of Borel sigma field, is it possible to find any relation between these two? And naturally the answer is yes. So equivalent of two definition, this is given in terms of a theorem, that x1 and x2, these are the two random variables, these are independent if and only if script b of x1 and script b of x2 are independent, and just similarly xt, t belongs to capital T, are independent if and only if script b of xt, t belongs to capital T, are independent. So let us try to prove this result. First, if part means we assume that script b of xt, t belongs to capital T, are independent. Now this immediately implies that consider for any collection t1, t2, tm belongs to capital T, and consider a collection of corresponding lambda values, that is lambda 1, lambda 2, lambda m, all lies between minus infinity and plus infinity. Then x of t1 less than equals to lambda 1, this belongs to script b of xt1, and so on. X of tm less than equals to lambda m belongs to script b of xtm. So if we consider the joint distribution function of this collection of random variables, that is joint distribution function of xt1, xt2, xtm, which is given by capital F of xt1, xt2, xtm of lambda 1, lambda 2, lambda m, which is nothing but probability. This is just by the definition of joint distribution function. This is equals to probability capital X of t1 less than equals to lambda 1, and so on, capital xtm less than equals to lambda m. Now it is given that script b of x1 and script b of x2 are independent. That means xt1 less than equals to lambda, this set belongs to script b x1, and xt2 less than equals to lambda 2, that belongs to script b of x2. Since script b of x1 and script b of x2 are independent, so we can immediately say that these two events xt1 less than equals to lambda 1 and xt1 less than equals to lambda 2 are independent. So naturally from this line, that is probability xt1 less than equals to lambda 1 and so on xtm less than equals to lambda m, this is equals to probability of xt1 less than equals to lambda 1 probability of xt2 less than equals to lambda 2, and so on, probability xtm less than equals to lambda m, which is equals to, now individual term is nothing but the individual distribution function. So capital F of xt1 lambda 1 dot dot up to capital F of xtm lambda m. So this proves that xt1, xt2, xtm are independent. So given that that script b of x1 and script b of x2 and so on, they are independent, we have proved that xt1, xt2 and xtm, they are also independent. Now remember, m is finite, so any finite collection of random variables, they are independent. Now we have to prove the only part. That means assume that we are given x and y are independent. Now define a class of events G which is equals to capital F such that probability E intersection F equals to probability of E into probability of F, where F belongs to script B of Y and E belongs to script D of X. And let us call this as equation 1, where script D of X is defined as omega such that, all such omegas such that x omega less than equals to lambda, provided lambda lies between minus infinity to infinity. Now remember one thing, it is immediately clear that this script D of X is a subset of script B of X, or that is Borel sigma field generated by X. It is immediately clear also that G is a non-empty class, that means since G contains script D of Y. Now we are given that D of X, that is script D of X and script D of Y are independent. This is given. So now we have to prove that script B of X and script B of Y are independent. Now in order to prove this, it is sufficient to prove that G is nothing but script B of Y. That is, by symmetry it will immediately follow. So to prove this, we need another definition and two important lemmas. Let us first define that, consider the definition. Let G be a non-empty class of subsets of omega. We call G as a pi system if A comma B, if two sets A and B belongs to script G, that will imply that AB also belongs to G. And G is a lambda system if three conditions hold, that is omega belongs to script G, A and B belongs to script G imply, and B is a subset of A. This will imply A minus B belongs to script G. And if we consider An, for every n belongs to script G and An increases to A, this will imply A belongs to script G. So if these three conditions hold, we call G is a pi system. Now note one important thing is that it's a clear observation that if G is a pi system, if G is a lambda system, then for A and B belongs to script G and A intersection B equals to phi, it is immediately clear that A union B will also belong to script G. Now lemma 1, this is known as Dynkin's pi lambda theorem. If a lambda system G covers a pi system D, then G contains script B of D, that is Borel sigma field generated by the system D or script D. And lemma 2, second lemma is if script D is a pi system and G be any non-empty class of subsets of omega, let us consider this, then we can say that if script D and G are independent, then script B of D and G are also independent. So naturally it is clear that lemma 2 is very important in proving the only part of the previous theorem. So the proof of the theorem now follows immediately from these two lemmas. Now remember one thing, this script B is nothing but the Borel sigma field generated by script D, and G is defined, G is given in the previous definition. What's it? Oh, acha. So note that we are going to prove that script B of script D, that means Borel sigma field generated by script D and G, they are independent. Now it is immediately clear that this gives us the idea of the proof of this only part of the previous theorem, which we are going to do in a formal manner immediately. So proof of the theorem, which is the only if part, it is given that x and y are independent, that means two variables are independent. Let us define script G, which is the collection of f such that probability of E intersection f equals to probability of E into probability of f. F belongs to script B of y and E belongs to script D of x, where script D of x, as we have already mentioned, that collection of all such omegas such that x omega less than equals to lambda, where minus infinity less than lambda less than infinity, which is a subset of script B of x. Note that it is immediately clear that script D of x and script D of y both are pi systems, because intersections of semi-closed intervals are also semi-closed. Now it is easy to show that this G in 1, that the way we define script G is also a lambda system which contains script D of y. Now there is nothing more to prove, because lemma 1 and lemma 2, application of lemma 1 and lemma 2 actually gives us the proof. So the proof of this only part is complete. That means now we have a very strong idea of this theorem that we can define independence in terms of random variables, as well as we can define independence in terms of Borel sigma field generated by those random variables, and we have shown that these two definitions are equivalent. So today we have discussed some definitions of independence. First we started this introducing the definitions in terms of events, and later move on to defining this concept of independence in terms of random variables. But as we already mentioned at the very beginning, that it is essential to define independence in terms of some bigger class of events. In this case, by bigger class we mean some kind of sigma field or Borel sigma field generated by the random variables. And we have seen also that we can define, this definition can be extended to such classes, such bigger classes of random variables or classes generated by random variables. And we have also proved one theorem stating the equivalence between the independence of random variables and independence defined with respect to the Borel sigma field generated by random variables. This actually led the path to further development of some other important theorems and laws and lemmas in the probability theory, which would be again extremely useful in proving or developing some interesting theorems and results in the area of convergence in probability theory. So this independence is an extremely important thing, and we need to understand the meaning of independence very clearly from several perspectives. That's what we did today.